Hello, everyone. I am so happy to see you all here, and I feel truly honored to be able to present to you a problem which I currently face. Let me introduce myself real quick again. So my name is Wojtek. I am a computer science student at Warsaw University of Technology, and I've been working in a data science agency where we have some pretty unconventional internal projects, and one of them is modeling emotional nuances of piano performance. This is more of a scientific project than a commercial one, but I'm sure it is worth exploring, and I'm sure some of you will agree. Pythagoreans believed that all nature consists of harmony arising out of numbers, and they are believed to be the first ones who investigated mathematical relationships underlying musical intervals. Throughout history, people have found beauty and meaning in the connection between mathematics and music, and there has always been some mathematical way we go about making music. Think about beats of ancient cultures or melodies of classical symphonies or even chord progressions in modern jazz or pop music. Algorithmic music composition is taking this mathematical way to an extreme. And the most often cited examples of algorithmic music composition in classical period is Musikalisches Würfelspiel by Mozart. In this composition, he created discrete musical accepts which could be combined to form a waltz, and the order of these accepts was determined by rolling two six-sided dice and referring to a table which looked like this. In 1957, Leger and Hiller and Leonard Isaacson programmed the ELIAC computer at the University of Illinois to algorithmically create music. And the output of the software was one of the first compositions made with a computer. And have you heard about John Cage? Anyone? Please raise your hand up if you did. Well, great to have you here. For those of you who don't know, John Cage was the man who wrote 4 minutes 33 seconds, which was 4 minutes and 33 seconds of silence. Just to give you an idea. He collaborated with Hiller to create his own algorithmic composition using a computer called harpsichord. And this is not something you'd want to listen to on your way to work. It turns out that making a composition with a computer that is also aesthetically pleasing, not only thought-provoking, is no easy task. And Mr. Cage was actually much more interested in intellectual value of art. He once said, "It is the machines that will help us to know whether we understand our own thinking processes." And with today's innovations and rapid development of machine learning methods, it is high time for another shot at algorithmic music composition. And I strongly believe that the door to mathematical nature of music can be opened with machine learning. And we decided that the journey to discovering this mathematical nature of music inevitably starts with a piano. So a piano keyboard, comprises 88 keys, each responsible for producing a distinct pitch, and the pianists press the keys with varying velocities. The higher the velocity, the louder the sound produced. Therefore, we can look at a piano keyboard as an interface with 88 keys. And much like a computer keyboard, and just as computers react to a press of a computer key, pianos react to a press of a piano key. In particular, pressing a key down right here causes the hammer to go up and hit the string. There is a lot more going on, but let's focus on that. The base hypothesis driving this project is that the input to this piano interface has a lot of similarities with a natural language. And just as words and sentences have structure and meaning, sequences of note presses, of key presses and their velocities create musical phrases and expressions. And what is great about piano music is that the data from the performance can be obtained directly from the keyboards. Much like any computer can obtain exact information on a key press. This is much harder to do with other instruments, like a guitar, for example, where musician operates directly on strings and does a lot of tiny little tricks to modulate the sound. And there are a lot of technical nuances that come into play. A piano is more of a machine. Pianist press the key and a note on event is processed. He releases it, a note off event is processed, and so on. So two notes are played, two rows appear on a data frame, or two rectangles appear on a piano roll, which you can see at the bottom. And MIDI can be represented as a table of notes, and each note can be described with 4 values: pitch, or number, or a key number, which ranges from 21 to 109 on the piano; velocity, which is also an integer ranging from 0 to 127 in MIDI; and start time and end time, which are floats, which gives us accurate representation of a performance. This is piano performance by Yu Wong playing Flight of a Bumblebee. Notice how much information is being forwarded with the help of a piano interface through pianist's fingers, and how the composer's intentions manifest in a form of notes and sounds. Imagine it as a data stream. This is a continuous flow of key presses and releases separated by mere fractions of seconds. Each press carries its own distinct velocity, dictating the loudness of the sound. And the pianist's fingers are navigating this stream with precision and finesse. The MIDI format enables us to store the exact information about the relationship between the artist and the instrument. And when modeling performances, we are interested solely in this interaction. We want to model the data describing this particular relationship to train models to use this piano interface. And because of this interest in mechanical aspects of a piano performance, MIDI is a far better tool to use than audio format, primarily because of the data size. In MIDI, instead of standard 44,000 audio frames per second, you get less than 10 notes per second on average. This is a spectrogram, a view of the frequency content of an audio wave. The brighter the color, the higher the amplitude or the power of a sound wave of a particular frequency. And if you worked with audio before, I don't know how many of you did, piano rolls are much like spectrograms. They provide a view of they are visual representation of a MIDI file. And you can already see that the MIDI format is much smaller. There is no information on the nature of a specific instrument, no information on timbre or acoustics of the environment, just the relationship between artist and the instrument in a digital format. And although it is much less information than audio, because we know that a piano was used to play this piece, we can play it back using a digital piano. But that level of extraction is also a double-edged sword, as pianists can modify the way they are playing a particular piece to the specific instrument they are using at the moment, and the nature and the acoustics of the surroundings. Also, pianos feature pedals, which can be stored to some extent in MIDI format, but they complicate the translation to data frames. And for initial experiments in the spirit of first order approximation, I removed the use of pedals completely. So it is worth remembering that there is still a lot of information we do not store, but nonetheless, human performances can be very accurately recreated with just the MIDI data in this representation, despite these problems. And here is an example of such representation. So for now, the data focused primarily on a piano keyboard interface is more than enough to run some very interesting experiments that we can upgrade in the future. And to convert a raw MIDI file to a form of a data frame, we can use tools such as the fortepian library, which is open source, This is kind of which is open source. And each entry in the data frame corresponds to a note plate and includes pitch of the note, velocity, and timing, just like I showed you before. And thanks to the quality and accuracy of MIDI files, they are great for analysis of the emotional nuances of a piano performance. But what exactly are those nuances? Can anyone read sheet music? Please raise your hand up if you do. Wow, it's great to have you here. I hope you agree with me when I say that composers use score music as a way of storing data, right? So pretty much. And musical scores operate themselves within a language of musical notation. And the sequences of notes on a score sheet provides pianist guidance on when to press and release each key. And the timing is aligned to a relative metrical grid, so quarter notes are the same duration as quarter notes rests, and twice the duration as eighth notes, and so on. And there are also quite a few written instructions that could be put on scores. For example, espressivo, between the shelves, guides the pianist to play with an expressive quality, whatever that means. Largo, over the top shelf, means slow and broad, or broadly. It indicates that the piece should be played at a very slow tempo, like 40 to 50 beats per minute. But the exact timing and velocity applied to each key is left to the performer's discretion, who should try to interpret composer's intended mood and sound. And the interpretation can be influenced by factors such as genre, historical period, or other conventions musicians use. So there is a whole universe of problems a pianist must face in order to make a correct interpretation. By the way, this is a piece by Chopin that and it is featured in The Notebook with Ryan Gosling and Rachel McAdams, so maybe you've heard it before. Here you can see two piano rolls. The one on the left is deprived of any nuances of a piano performance. It is raw mechanical translation of the notes, and it sounds like this. But the same scores can be interpreted by a human to sound like this. And I hope you can hear that it is much different from mechanical translation. This is the real performance we want our model to be able to play, and this is language we want it to speak. Different pianists can interpret a piece in completely different manners, and it is their interpretation of the composer's intentions that puts soul into the piece. For example, here you can see note duration distributions between two performances of the same piece. And you can see the differences in the interpretations. And here is the time difference distribution of two performances of another piece. Time difference meaning time difference between consecutive note presses. The crux of the matter is there is a finite number of symbols with which a composer can operate in order to describe what his intentions. And the interpretation of the scores, it's what makes the performance magical, and articulating what the composer had in mind is much more complex than what he can describe on a piece of paper. High quality data, loaded directly from the keyboards and packed with nuances of piano performance, can be found in, for example, in Maestro datasets, which is actually a TensorFlow Magentas dataset, composed from piano performances from piano competitions. It contains about 200 hours of classical piano music, which is equivalent to 7 million notes. And it served as the backbone of our own datasets and our experiments, our initial experiments. And we have our converted version on Hugging Face, which is awesome for storing and managing datasets. We can browse the dataset and then visualize and listen to a MIDI file using Streamlit and a Streamlit component called Streamlit Piano Roll, which is also open source. Yeah, and here you can see an example of what we can find in the dataset. For example, yeah. So when we have a MIDI file in a format of a data frame, we can perform some general analysis like we are used to do. For example, here you can see that among the pieces played in piano competitions, those written by Beethoven tend to have much shorter notes than those written by Chopin. Other fun things to watch are pitch distributions across pieces written in different musical keys. And when we say a piece is in a certain key, we mean that it is based on the notes and chords from that key, giving it a particular sound and emotional feel. Given our piano interface, a musical key would be a subset of available keys among the 88. So you can see the difference between which notes are being used the most often in the key of D minor and the key of D sharp minor. In terms of natural language processing, we could compare it to the text style. Formal language will use a different set of words than informal, etc. Moving on to large language models and training large language models, a typical large language model training pipeline includes gathering data, tokenization, and training the model. And MIDI data available on the internet is slight, so we need to think of other ways of gathering the data. There are lots and lots of different methods for tokenization, which gives us a lot of stuff to experiment with. And the training involves a typical next token prediction or basically any other task that you can think of. And the initial plan was simple. We wanted to train the model to, the entirety of GPT training pipeline can be learned from Mr. Kapathi on YouTube in a 4-hour coding session. The initial plan was simple. We wanted to generate sequences of notes from input sequences of notes, so a basic sequence-to-sequence task. Unfortunately, with our initial vocabulary definition, which was to use 1 token per note, we were not able to generate anything interesting. We experimented by only treating note pitches as a language and using vector quantized variational autoencoders or diffusion models for timing and velocity. And you might know diffusion for its use in image generation. It involves adding a rising level of noise to the data, as you can see in an example of a cat. And the idea is to later generate data from pure noise. We tried diffusion models on velocity values. The bottom axis is the level of noise we inject into the piece, and it sounds like this. Right, so this is really interesting stuff, but unfortunately, these experiments have led us nowhere yet. If you are interested in the details, please give us a call and we will be happy to talk. In the meantime, we reverted to our original idea and redefined the vocabulary. And that did the trick. We trained a GPT-2 model to generate continuances of musical fragments. And there are terabytes of text on which large language models can train. GPT-3 was trained on approximately 300 billion tokens, and GPT-4 allegedly 13 trillion. So the Maestro dataset mentioned earlier consists of 7 million notes in only 85 megabytes of MIDI files. But for the past few years, my company actually has been employing and collaborating with professional pianists who shared recordings from these practices. And that combined with data from publicly available sources served us for our pilot projects. And right now, our largest dataset consists of around 200 million tokens. which is similar size to what an original transformer from Attention Is All You Need paper trained on. And this is pre-augmentation. And there are many methods, many augmentation strategies we can use. For example, pitch shifting is a great technique because the musical pieces can be played with pitch shifted left or right by a constant and still sound right. Here you can see the distribution of pitch values before and after a one-step shift. Another popular augmentation technique is to change the tempo of the piece. For example, a piece that is 3 minutes long after a 5% reduction would be 2 minutes 51 seconds long. And the difference is so slight it is practically unnoticeable, but there's real dataset enhancement. Moving on to tokenization, in natural language processing, there are a few steps before we can pass a random text found on the internet to the LLM. And this model step you can see on the slide uses a tokenizer model to feed to data and create optimal vocabulary. So it creates merges of characters to describe tokens. And please, again, raise your hand if you trained and used Hugging Face Tokenizer before. Nice, great. So you probably know what BPE tokenization is doing. BPE algorithm searches common merges of characters inside the words to create an optimal vocabulary. For example, this today word would be tokenized by a trained BPE tokenizer as 2 tokens because this today word rarely occurs in the data. So using BPE enables text tokenizers to tokenize unknown and uncommon words with multiple subword units. And what is exciting about using LLMs to model sequences from completely different domain than natural language processing is that we are the ones who are defining the language and the symbols and the alphabet. So we are given precise control over how we pass the data to the model. And to describe notes with symbols, we need to tokenize floats. We first need to apply some level of quantization to the recordings. And quantization comes down to rounding up the values to a desired granularity. Here is an example. Each velocity and time column got quantized into a specified granularity, and quantization to a few milliseconds should have no aesthetical loss, more or less. Pre-tokenization in natural language processing involves using some naive approach to tokenize text, like splitting on spaces. And for training a GPT model, we tokenize the MIDI data into indivisible symbols first. So you could say we use character level tokenization. Each of those symbols describes one of the values that build the note or a time difference, and they can be successfully used to train the model as well. To transcribe time differences between the key presses and releases, we used a set of symbols describing time differences rising exponentially. And here is how this transcription process works. One row in the original data frame corresponds to one note played, right? And we divide each note into 2 separate events. And this is more like in an original MIDI format. And each event is described with event type, time, and velocity, and the pitch. And each time is original start time for note on events and original end time for note off events. And first we transcribe velocity value. Then, according to the event type, we put an adequate event token, also describing which pitch value was used. Then we calculate the time difference to the next event and put an adequate time difference token. Then we move on to the next event, and so on. So the next time difference is less than 10 millisecond threshold, so we do not put any time difference tokens, and we move on to the next event, and so on. And we can put multiple time difference tokens between the events. The process continues until we are eventually left with transcription of a MIDI file, and the data loss is, the information loss is practically unnoticeable. So these two pieces sound exactly the same, at least for me. And so the set of symbols we use in this step defines our alphabet for describing musical sequences. Again, in natural language processing, BPE tokenizer creates subword units, but in MIDI, we actually use BPE tokenizer to merge the tokens from an alphabet together. Because the tokens we have are already indivisible, just like Unicode characters in text. So, and again, this is just one of the possible approaches to the problem of tokenization and passing data to the model. And this method enables us to downgrade the amount of tokens we need for transcribing, for example, 1 minute of Chopin from 1 minute to 1 minute of Chopin from 5,000 tokens to like 2,000 or so. We chose to train GPT-2 architectures. There are already repositories on GitHub. Oh, this is vocabulary example of BPE tokenizer. There are already repositories on GitHub you can use for optimal GPT-2 training. For example, NanoGPT by Kapathy. But there are tons of architectures one can try, like BERT or T5. We trained around 20 models, which each took somewhere around 12 GPU hours to train. And the results look and sound like this. And the blue notes are prompt and yellow are model generation. So whether it sounds like a plausible continuation of the sequence, I leave it up to you to decide. But by concatenating notes generated from different excerpts of piano recordings, I was able to conduct some analysis of model outputs. By comparing the pitch distribution of the original and generated notes, we can approximate that the model generations are somewhere within the same musical key as the original piece. So overall, the results, overall the results are still rather off, but promising. So we can clearly see and hear that some of the models accurately adjust to prompts to produce sequences in similar style and tempo. They also seem to remain in a specific musical key, which is of huge importance if we want the generated sequences to sound any good. So, plans for the future. Considering that training GPT-3 took around $5 million and the largest model is about 175 billion parameters, and was trained on 45 terabytes of text, I'd say the experiments we can afford to run and which are possible with currently available MIDI data are very limited. Nonetheless, there are a lot of experiments to run, and the cost of training LLMs drops in time. So maybe in 10 years we will be able to train a GPT-4 model for like $10. I also have this dream of building a community of data scientists who are willing to face the problem of modeling emotional nuances of piano performance and modeling MIDI files. So right now I am developing benchmark tasks to evaluate and compare the models, and one of those tasks involves predicting a subsequence of notes from a sequence of notes deprived of it. So we simply filter the notes on the pitch value and make the model train to predict, for example, only the lower notes. The blue notes would be the prompt and the yellow notes would be model output. And what is interesting about this problem is that it showcases models' understanding of harmony and musical structure of the piece. There are also a lot of open problems in modeling piano performances. One of them is defining a musical word for pre-tokenization step instead of using individual characters. Another problem would be defining effective metrics for tracking training progress and comparing models. Such metrics would be assessing tempo consistency, but by approximating beats per minute, or checking whether the model uses pitches from the same key as the rest of the piece. The fortepian library and the Streamlit piano roll component are open but not ready, and you can find them on GitHub. And to create an algorithmic music generator, we may also train models all on algorithmically generated music, and that way we could combine the mathematical beauty of algorithmically generated music with real audio performances. And I encourage exploration into creating such algorithms, not only those based on neural networks. When you do, you can share your compositions on our social media platform, because our company is closely connected with the music and pianist community, and the photos you could see were actually from our recording sessions with musicians we collaborate with. So we've developed a social media website where pianists can share their recordings in MIDI format. And it is a place for them to socialize and find motivation for practicing, but it is also a place for algorithmic music enthusiasts and machine learning enthusiasts like me to share their algorithmically created music. We are even thinking about turning it into a competition in the future. And for us, apart from creating a wonderful artistic community, it is also a way of obtaining crowdsourced data for training new models. With the help of pianists willing to share their recordings, we might be able to gather the amount of data needed for exploring this musical world of music. So, getting to conclusions, piano music is an exciting and rich universe of artistry and mathematical relationships, and we've learned that transformer-based architectures, though in the early stages, show some promise in decoding the mathematical nature of music. By building communities and sharing knowledge and taking advantage of the newest technologies, we can explore this intersection more. And I think that with our collective efforts, the future of algorithmic music composition does seem bright. And I'm really excited to see what can be achieved. And most importantly, we will be discovering and understanding the mathematical nature of music as humans have been doing for centuries. Thank you very much. Thank you for your attention. You can check out our company at eprlabs.com. The repository for this presentation can be found on GitHub under MIDI PyData London 24. You can also check out our organization GitHub with some tools that we use and experiments we've run. You can reach out to me to ask questions at wmatej14@gmail.com. You can also catch me later during the lunch break or after this talk. I will share all the links on Slack later. I yet again invite you to explore and play with MIDI and share your compositions on piano roll. And if you play the piano and want to help in sourcing the data, I am sure you will find it fun to track your progress there. I don't know if we have time for questions. Okay, I will take questions now, but I can also show you some more generations if you want to, model generations, if you are interested. Okay.